every 1 centimeter monitor the soil properties. And for this reason, some hydrologists think that the term spatially physically based is misleading. Some hydrologists say that there is no physically based model in hydrology. There is always some level of approximation due to lumping processes, heterogeneous processes at a finite spatial scale, which comes into play. So approximation due to the fact that in any case, the control volume, even if it's very small, is never infinitesimal. But in any case, I think from a didactic point of view, this subdivision, black box conceptual physically based, is clear. We have an increasing level of detail and an increasing complexity. And as we move forward to our ideal aim to perfectly reproduce hydrological processes. Another very important distinction is between event-based versus continuous simulation models. What is the difference? At the beginning, rainfall runoff models were conceived to support the design of flood control structures. About 150 years ago, people became increasingly concerned by floods. And the reason was that people started to live in close proximity of rivers. With the evolution of society and the advent of industries, people got closer to the rivers, and they were increasingly concerned by floods. And therefore, the first problem was not really water resources management. This is a problem that came later, as you know. The first problem was flood control. And people started to elaborate rainfall runoff models to estimate peak flows, not to estimate the whole regime of river flows, just to estimate the peak flow. And then they tried to build models that were able to reproduce only the peak flows, not the full hydrograph. And so this is the reason why they restricted their attention to small events, small in time, short events, let's say. They didn't care about reproducing the river flows along the whole year. They wanted to reproduce the river flow only in the rainy season, in the flood season. And therefore, they tried to build models that reproduced one flood event only. So this is the reason of this classification, event-based models. And of course, there is an advantage. If you reduce the time span covered by the model, you reduce complexity. And also during floods, you may neglect some processes like evaporation. Evaporation is not really influential during floods, because during floods you don't have much. You are not experiencing high temperatures, and evaporation is reduced. And besides that, the effect in terms of volume of water evaporated, of evaporation on a flood is really negligible. So you can forget evaporation during floods. But later on, with the increasing needs to simulate the whole hydrograph for water resources management purposes, brought people to devise continuous simulation models, which means that they can run for years to reproduce like 100 years or 1,000 years of river flows. And of course, these models are more complicated and require more computational resources. And then you already know the distinction between simulation models versus forecasting models. I already made clear this difference. Okay, now, what is a parameter? It is an important behavior of a model. And parameters usually appear in the model's equations. And I want to give you an example. For instance, if you want to describe how water moves along a river, roughness is an important parameter. Roughness, if you have an high roughness, water moves slower than what happens when you have a low roughness. This roughness is extremely important. And it's a physical property. Roughness is a physical property. but because of the fact that you cannot measure roughness, you can measure roughness in ideal condition. If you build a small channel in a lab, then you can measure roughness. But if you go along a river and you look at the river, it's impossible to measure roughness. And therefore you have to estimate roughness, meaning that you build the model, you assume that the model is good, and then you put roughness as an unknown. Roughness is scabrezza in Italian, just to be clear. You put roughness as an unknown, and then what you do is to estimate roughness by optimizing model performances. So you introduce something that is called a parameter, which is related to a physical property, but indeed it's something different. So you introduce a parameter, and then once that you build the model, you estimate the value of the parameter by optimizing model performances. This is also called model calibration, optimization, fitting. Model calibration, model optimization, model fitting, they are synonyms. So what is a parameter? It's not easy to define what a parameter is. I made you an example which is relatively easy to understand, but if you want to provide a definition, what is a parameter? A parameter can be defined as a constant or a variable term in a function. It can be variable because roughness, think about roughness. Roughness is different depending on the season. When you have vegetation that grows, you have an increase of roughness. And then in the dead season, you have a decrease of roughness. So roughness, a parameter can be a constant or a variable term. Variable in time. In a function, which is typically a model equation, that determines the specific form of the function, but not its general nature. What is the meaning of this? If you want to describe the river flow, depending on roughness, you apply, basically, as you know from hydraulics, two equations. One is mass balance equation, and the second one is energy balance equation. Roughness comes into play in the energy balance equation. So the general nature, the general form of the equation is an energy balance. But the specific form of the equation depends on the parameter. So the parameter determines the specific form of the equation. Because of course, if you have an increased roughness, you have a higher dissipation of energy. So the specific form of the equation is dictated by roughness, but not the general form of the equation, which is just an energy balance, independently of roughness. Or you may think to a very simple relationship, linear relationship, fx is equal to a parameter a that multiplies x, where a determines the slope of the line, but not the fact that this is a straight line. So this is a linear equation, it describes a straight line, so the general form is a straight line, and it's not influenced by a. But the slope of the straight line, which is a specific behavior, is dictated by a. Parameters might be present in physically based equations, like roughness, which is included in the energy balance equation. Of course, physical properties can be considered as parameters, like roughness, but usually the term parameter is reserved for quantities that are not physically measurable and compensate for approximation in the physical equations. So it's important to know that you have these parameters in a rainform of model. They are always present. There is no non-parametric version of rainform of models. Here I'm sorry that the screen is cut, but there is just written calibration and validation. Calibration, I already introduced it to you. Validation, let's postpone it. Okay. Some more considerations. Development of a rainform of model depends on the time scale and the basin scale. What does this mean? That depending on the time scale that you want to describe, like you want to describe river flows at hourly, daily, weekly, monthly, annual time scale. So depending on this need, and depending on the size of the watershed or basin, so small basin rather than a big basin, the model changes. With short time scale, the shape of the yetograph is very much significant, which means that if you want to operate at short time scales, the way in which rainfall occurs is very much significant. While if you operate at the annual time scale, it's important for you just to know the annual rainfall, not really if it rains in February rather than in December. But if you work at shorter time scale, it's important to know the shape of the yetograph, to know rainfall in detail. And then a small basin, this is another important feature. Operate a less significant filtering effect on rainfall. What does this mean? If you have a short basin, the shape of the hydrograph is close to the shape of the yetograph. If you have a huge basin, then the filter operated by the basin is more significant. These are all considerations related to the relationship that occurs between catchment forms and the river flow regime, and are considerations that are useful to try to better understand this relationship. Linear models, there are many rainfall runoff models which are linear, and why we consider linear models? Because they are simple. They are very simple to apply. But indeed, the rainfall runoff relationship is not linear. Because, linearity means, first of all, what is a linear model? Let me just provide a definition. If you have a linear model, then f of a plus b is equal to fa plus fb. This is the superposition effect. It means basically that the effect of a rainfall given by two contributions, the effect of a yetograph given by two contributions A and B can be given by the only sum of the two single river flow given due to each single contribution. This is, of course, not true, because we all know that if you have a huge rainfall that falls over a dry soil, you don't see any flow in the river. You may not see any flow in the river, but once that the soil reaches saturation, even a small amount of rainfall can cause a flood. This means that it's not true that the effect of the sum of two rainfalls is equal to the sum of the two river flow due to each individual rainfall. This is not true, because there is soil moisture which is playing a relevant role. So the effect in terms of river flow of a rainfall depends on soil moisture, which makes the relationship non-linear. And also there is a second condition, which is FAX is equal to AFX. These are necessary and sufficient conditions for a model to be linear. So, as I said, for sure, the rainfall runoff relationship is not linear, but linear models are usually applied because they are simple. The linear approximation, as you can read here, may be appropriate for short time scale, is not appropriate for short time scale and small spatial scales. As you refer to increasing spatio-temporal scales, then linearity becomes a reasonable approximation. But if you go down to short time scale and small spatial scales, linearity is no more a reasonable approximation. Constant in time and spatially uniform rainfall, it's an approximation. You see that typically induces a S-shaped hydrograph in the long time. This is a well-known behavior of watershed, which means that take a watershed and apply a rainfall. Let's call it RT, which is constant and very long. What is the effect in terms of river flows? It is what is called a S-shaped hydrograph, which means that, let's specify a limiting flow. The hydrograph has this shape. Why this? Because you have a slow increase of river flow at the beginning of the rainfall, because much of the rainfall infiltrates, and then you get close to saturation. You have a rapid increase of the river flow up to a maximum. The maximum is reached after saturation and represent the maximum flow from the watershed in reply to the given rainfall. This is important to understand basic watershed behaviors. Again, it's important to gain a full comprehension of the rainfall runoff transformation on a perceptual basis, because this helps you to build the model. And my suggestion is go out and look around, especially during floods. If you get the news that a flood is occurring, it's interesting to go there and see, because by looking at the river during a flood, you really understand what's going on. But in general, it's very much appropriate if you want to gain a good experience in hydrology, just to look around when you see rivers, when you see water flowing, just to try to better understand how water flows, how a catchment reacts to water, sometimes maybe to rain, maybe that you are like hiking during a rainfall, and to look at how the rainfall flows toward the river helps you very much in understanding a perception of how water flows, how the river flow is forming. So let me give you a first example, which is very, very, very relevant, although very, very, very simple. It is the rational formula. The rational formula was the first attempt to build a rainfall runoff model. People are debating who proposed it. I put here the reference, Kuchling, 1889, but Irish hydrologists claim that it was first proposed by an Irish, of course, engineer, called Mulvaney. I don't know how to pronounce it. And accordingly to them, Mulvaney proposed the rational formula in 1859. So US people tend to state that the proposer was Kuchling, but Irish people say that it was their invention about 20 years before. The rational formula, which is widely used in engineering, can be considered a rainfall runoff model, although it's so simplified that in principle you don't need to refer to physical laws to elaborate it. So it can be considered a black box model, but indeed, as we will see, there is some physical basis, because it's basically a mass balance equation. And The reason why I wanted to postpone the treatment of the Reynolds transport theorem, which is a physically based equation, is that I wanted to show you before that it's in principle possible, and in fact, historically people did so. It's in principle possible to derive, to write a Reinforth model without resorting to any physical equation. So what is the essence of the rational formula? The rational formula recognizes that there is, first of all, it aims to reproduce not the full shape of the hydrograph, but just the peak. You don't see any dependence on time here, just a subscript p, which means peak. So it was aimed because, as I said, the practical need of those people was to estimate the peak flow, not the full hydrograph. And they had the problem, the typical problem was, I have a river, I want to estimate the peak flow of this river, because if I want to build a bridge, if I want to build a levee to mitigate the risk of flood, of course I need to get an idea of the maximum flow that I may expect from the river. And they had the problem of having no observations at all at that time. So the idea was to start from rainfall, because they had a better knowledge of rainfall. And the idea was that the peak flow depends from rainfall, intensity of rainfall, the basin area A through a parameter C, which of course provides a linear relationship between the product of rainfall times area and the peak flow. Basically, the relationship starts from one very simple consideration. If you have a river basin and you have a rainfall, let's call now E, intensity, that forces the basin, and you know the area of the basin, then it's very simple. By multiplying the rainfall intensity times the area of the basin to compute the volume of water that flows, that rains over the catchment per unit time, because rainfall, what is volume, is height, depth of rain per unit time. Rainfall intensity is expressed typically in millimeters over time, and it's depth of rain per unit time. If you multiply the depth of rain times the area of the catchment, you get the volume of rain that occurs over the catchment per unit time. And of course, this is the maximum value that can be attained by the river flow if you don't have any water losses. So if you don't have any water losses, the product rainfall intensity times area of the catchment is the maximum value that can be attained by the river flow. So it's clear that this product is strictly related to the peak flow that you can get from a catchment. And of course, given that this is the upper value that can be reduced, for instance, if you have water losses, if you have evaporation, if you have a situation in which not all the catchment is contributing at the same time, then it's appropriate to introduce a factor C, which is typically lower than 1. And please pay attention to the last thing that I said. If you don't have all the catchment contributing at the same time, because if you take the product of rainfall intensity times area of the catchment, you are implicitly assuming that rainfall is occurring over the whole catchment. Instead, it might be that there is a part of the catchment without rainfall. In reality, this occurs. So you are assuming that the rainfall is occurring over the whole catchment, and if you take this product as an estimate of the river flow, you are making another implicit assumption that the whole catchment is contributing to the river flow. And let's make this concept clear. If it starts raining over a catchment, let's assume that all the catchment is heated by the rain. What do you observe? You observe that the river flow starts to gradually increase. For instance, after 1 hour, you see that the river flow is increased. Why it's increased? It's increased because the part of the catchment that is closer to the river cross-section where you are looking to contributes to the river flow, meaning that the rainfall that falls here reached the river flow, the cross-section. And given that it's continuing raining, this part of catchment is contributing to the river flow after 1 hour, for instance. But this also means that the remaining part of the catchment is not contributing because the rain that has fallen here did not reach yet the cross-river section. After 2 hours, you may see that another additional part of the catchment had the time to reach, water at the time to reach the river cross-section. So a higher portion of the catchment is contributing to the river flows. So basically, if you take this product and you assume that this is the river flow, you are assuming that the whole catchment is contributing. And this happens only after a certain time. Is this concept clear to you? So you are making the implicit assumption that it's raining over the whole catchment, and the whole catchment is contributing to the river flow. Given that, you know, this is an upper bound for the river flow, it's from a practical point of view, it's appropriate to introduce a coefficient C, which is in practice lower than 1. Because you may have some water losses, you may have that the rain is occurring not over the whole catchment, and you may have that the catchment is not totally contributing to the river flow. So this causes a reduction of the peak flow, and therefore it is appropriate to introduce this coefficient C. So this is the rationale behind the rational formula. QP equals C E A. But indeed, this is a very reasonable formulation. If you had an estimate of the maximum rainfall that can occur over a catchment, this is a very reasonable approach to estimate the peak flow. And keep in mind that in some cases, people noticed runoff coefficients, because this is the name of this parameter C. It's called runoff coefficient. People noticed in some cases runoff coefficients higher than 1. Why that? It's possible. Think, for instance, to the case in which part of the catchment is covered by snow. And think about an increase of the temperature. You may have a flood even without rain. Or in some cases you have the so-called rain over snow effect, which is the cause of many floods. Because you have a relatively reduced amount of rain occurring over a snowpack, and therefore snow melting is induced and you have a flood. Even with so during an event, you may have a runoff coefficient greater than 1, because you have some water that was already stored in the catchment in the form of snow, in my example, which contributes to the river flow. And also there is another reason for the runoff coefficient higher than 1, which is an erroneous estimation of the catchment area. Because you may jump into problems like the one I mentioned before, where the catchment divide is not a good indicator of the real divide between the waters. And therefore the catchment area is erroneously estimated. Be careful, the rational formula is linear, you see. If you put here a sum of two intensities, you have that the river flows, the resulting river flow is given by the sum of the river flows due to any single rain intensity. So it's linear. And then you may understand that at a small spatial and time scale, it may be not really appropriate. What is the problem here? The problem is not the estimation of the catchment surface, which of course may be difficult, but in general we can solve it quite easily. The problem is not the estimation of the rainfall intensity. The big problem is the estimation of C. Because if you make an error in C of 20%, it translates in an equal error in the river flow. So an error of 20% in C implies an error of 20% in the river flow. And you know, we know that the C is typically lower than 1, but it's not easy to estimate it. And if you take a precautionary approach, a conservative approach of putting C equal 1, you obtain probably a river flow that is overestimated, like 100%, 200%. If C is 0.5, and you assume, by adopting a conservatory approach, that it's 1, you overestimate the peak flow of 100%, which is an enormous amount. So with the rational formula, this is the big problem. And sorry, before I move forward. There is another problem here. What kind of rainfall intensity should I put in? Because, you know, rainfall intensity is varying depending on, first of all, on what extreme, how much extreme is the rainfall. So, of course, I may say the maximum rainfall that I ever observed over a catchment. But given that I have a very limited amount of observations, the maximum rainfall that I observed could be not really representative of a peak rainfall. Let's assume that you have 20 years of rainfall observations. If you take the maximum, it's representative just for 20 years, but you know, next year you may experience a higher rainfall. So rainfall depends on how much extreme is rainfall itself. But also, rainfall depends on the duration of the event. If you have a very long rainfall in time, typically the intensity is lower than a very short rainfall, which usually has higher intensities. We know this. We know that during summer, rainfall is usually, in our climate, short. The rainfall event is short with a high intensity. You get that in a few seconds. While during the other seasons, during fall, during spring, you have long rainfall events which are not very intense. So the question is, should I put here, if I want an estimate of the peak flow, should I put here the intensity that corresponds to a long rainfall or a short rainfall? Because, you know, if you put the intensity of a short rainfall, it's a very high intensity, gives to you a very relevant peak flow. If you put the intensity of a longer event, you get a lower peak flow, which is more likely for a given catchment. It's more likely a short rainfall or a long rainfall, because of course you cannot take the precautionary approach of putting the highest intensity. You have to put a proper intensity. And this question is very much relevant, and to answer to this question, let's think to another issue that I just mentioned to you. I said, in order to the rational formula to apply, we should give to the basin the time to contribute entirely to the river flow here. Otherwise, I have to adopt a lower runoff coefficient. So, when you think about the duration of the most worrying rainfall, because this is the problem. In the rational formula, if I want to get an estimate of the peak flow, I have to ask myself, what is the duration of the most worrying rainfall, worrying in terms of floods? Usually floods in my catchment are given by a long rainfall or a short rainfall, and this gives to me the answer. So when I asked myself what kind of intensity I should put here, the intensity was short rainfall or long rainfall, I should look in the past, I should look at the catchment and say, what is the duration of the rainfall that is warning for floods in this catchment? For instance, to use a rainfall duration of 1 hour for the Po River would be really nonsense. We know that the Po River, floods in the Po River occur after very long rainy periods that last for 1 week. After 1 week of rain, then we get the flood of the Po River. Instead, if we look at smaller catchment, mountains catchment, we know that sometimes floods are caused by rainfall that lasts for 15 minutes. If we look at the floods in the Liguria region that occurred last year, or the floods that occurred in Tuscany in a few months ago, they were caused by rainfall events that lasted for tens of minutes, no more. So it's clear that the Po River, for the Po River, the concerning rainfall has a long duration. It's clear that for smaller basins, the concerning rainfall has a lower duration. Therefore, this is the question that we have to ask ourselves. Look at the catchment and understand what is the typical duration of rainfall that causes the flood. And this is the intensity that we should put here, corresponding to that duration. And people realized very soon what I just mentioned to you, that for bigger basins, the duration, the critical duration of rainfall is longer. For small basins, the critical duration of rainfall is shorter. This was an immediate consideration that people did, and the reason is that with a short basin, the amount of time required for the whole basin to contribute is shorter. Because rainfall